In this lesson, we will be looking at polynomials in both standard and factored form, and we will be continuing to deepen your understanding of characteristics. You'll be graphing them without a graphing calculator. And so we're going to start with something that I think is familiar to you. And I want you to write down what you know about these two math concepts, factor and remainder. You learned these back in elementary school, really. You've used them since then, and we'll be using these words today. So write down what you know about them. And then on this screen here, I have the graph of a polynomial function whose equation is shown. Write down what you know about this function from both the graph and the equation. And try to be specific and use good, precise vocabulary. On this one, we have been sketching polynomial functions in the previous lesson, so I think you'll be fine at finding the roots, identifying them and sketching them on this x-axis. You'll know what degree this is. You'll see that there's a negative in front. What does that tell you about the right-end behavior? What about the left-end behavior? Go ahead and give that a try. And then this one we want you to do on your own as well. What is the degree of this function? And there are roots, real roots. I believe there's a double, a triple, and a single root. What do you know about the right-end behavior, the left-end behavior? And go ahead and sketch it. Put the video on pause. Come on back when you're ready. So one thing that I wanted to point out about the word factor is it has to do with both multiplication and division. Just a simple example like 5 and 3 are factors of the number 15 because 5 times 3 is 15. But then I can do a division problem. 15 can be divided by 5 with no remainder. It can also be divided by 3 with no remainder, telling me that 5 and 3 are both factors of 15. Now, speaking of remainder, when you have a remainder, when you're dividing, and of course my remainder here is the number 1, what that tells you is that 4 is not a factor of 29, neither is 7 a factor of 29. So remainders give us some good information about the problem. It turns out we can be using these words when it comes to polynomial functions as well. We asked you to write down what you know about this polynomial function. See if there's anything you can add to what I said. I can see that it's a cubic, right, because it's degree 3. I can see that the maximum number of turning points is a turning point here and a turning point here is 2. Turning points is always 1. Maximum number of turning points is 1 less than that degree. The right end goes up and the left end goes down. I can visually see that with my graph. I can also see the right end going up because it's a positive leading coefficient. There's one real root, but because this function has 3 roots altogether, it tells me that 2 of my roots must be complex. So that's an important consideration. Then to sketch this function, I wanted to find out what are my real roots and what is the y-intercept. So from this factor, I have a root of 3. I have a root of 1 from this factor, -1, and -3. My y-intercept, I find that by substituting 0 in place of x. And I just did some mental math and I end up with -9 for my y-intercept. Now my right end is going to go down because of this negative, right? So my right end goes down. It's a 4th degree polynomial function, so my left end is also going to match to go down. All of these are single roots, so the curve passes through each root. It hits some kind of a turning point and changes direction, passes through this root, goes through the y-intercept, passes through this root, hits another relative maximum, we call it, or actually this would be one of the maximum, and then it turns, and it passes through this other root. Okay, then I asked you to graph this one, which had a triple, a double, and a single root. The triple root is at positive 1. The single root is at 5. The double root is at negative 3. My right end definitely goes up because it's positive. This is a 6th degree function, so my left end has to match and also go up. It passes through this single root right here, changes direction somewhere, and then it kind of wiggles around. Do you see this? It goes up, it flattens out at 1, wiggles around, and goes up. That's what we do with the triple root. It goes, kind of flattens, and then keeps going. It goes through this y-intercept, which I figured out was 15, hits some maximum point, or relative maximum, changes direction, and notice it bounces right there because it's a double root at negative 3. It doesn't pass through negative 3, it hits it and then turns. So hopefully you did okay with that. And I'm going to do one more example with you. And this one, we're asking you to sketch a polynomial function. Now, when we say the word sketch, we're talking about doing this without Desmos, right? Without a graphing calculator. So this one actually was quite difficult for me, and I'll tell you why. The first part of it wasn't too bad. We had to factor this, and I looked at it and I said, you know what? This is reminding me kind of backwards FOIL. And what times what equals negative 5x to the 4th? Well, I did 5x squared times negative x squared. What times what equals 3? I did 3 and 1. And I kind of fiddled around with this until my first two, outside and inside, and last two worked out to be the original. So that was all fine and good. Then I set each piece equal to 0. So right here, I added x squared to both sides, and I ended up with 2 real roots, 1 and negative 1. So that didn't give me problems at all. This thing here, to set this piece equal to 0, I'm going to end up with x squared equals negative 3/5. Well, when you take the square root of a negative, you're going to need I. So I have plus or minus square root of 3/5 I. So here's the problem there. Because it's a 4th degree polynomial function, it can have at most 3 turning points. I know that the right end goes down because of the negative. I know the left end goes down because they match. This is a single root, so it passed through 1. But I knew there had to be a turning point somewhere. And the y-intercept, when it's in standard form, is nice. It's just this constant term, so I knew it was 3. And to be honest with you, I really did use Desmos to try to interpret what happens here. That is not something that would be obvious, and so that's okay. When you come to a place where you have to go to Desmos to kind of rely on what to do, I understood this part of it, the y-intercept. I understood the roots. The turning point was not clear to me. So there you have it. All right, so that's just a little bit about what we kind of already know about polynomial functions. Where we're going with this is we're finding out about the factors and the remainder, and how does that help us graph polynomial functions. I'm going to end this video here, and then we'll take a look at the next section of this in the next video.